Hey everybody, how are you? Welcome to the Chill Zone, where Don Gillis condenses the facts of working with Opteon low GWP refrigerants. My name's Chris Piles, and I'm going to be joining Don today to help out. Thanks to each of you for taking the time to join us. We know your time is valuable. It's in the afternoon. There's a lot of stuff going on, and so we are honored to have you here with us today. So we appreciate it. The transition to lower GWP Opteon refrigerants is here, and now is the time to start getting ready for your customers' questions. And so that's really what all this is about. So that's what we're all here to do. Now, if you have any questions during this period of time, feel free to just go down to that chat box right down in the bottom on the corner and put in your question. We're going to take as much time as we can to answer your questions. Obviously, if there's 100 questions, we may not get to them all, but the intent is for this to be an interactive, informal training session. Okay, so we're here for you. So fill out your questions, send them in. Also, we're going to have some questions on our side. So occasionally we're going to stop to do a poll question here and there. And really what this does is it helps us kind of see what you guys are seeing in the field. So it kind of goes both ways, right? We're trying to learn about what you guys are seeing so we can help you out better. Now, this might be your first time here, or you might be a regular, but either way, grab a coffee, sit back, take some notes, and wait for Don Gillis to just compress all of this stuff into your head for about an hour. All righty, thanks a lot, Don. Take it away.
Thanks, Chris. You might have set the bar too high. Welcome, everyone. You had me chuckling, Chris. Condensing the facts with myself. A closer look at 454B is going to be our topic today. So we're going to walk through some basic stuff, basic to probably most of you, but just to kind of reassure everybody's on the same page moving forward. This will be primarily, obviously, for the air conditioning folks. I was telling somebody earlier, I assumed, when I shouldn't assume, but when we first started the first episode, that most of you, if not all of you, or some of you anyways, knew who I was. So just a brief thing. I don't want to read all of these, but I'm Don Gillis, obviously. I'm the senior technical trainer here at Chemours, and I spent about 33 years in the industry, and 25 of those years were probably the most important years, and that was in the field. And I'm still a licensed journeyman, and worked around contractors pretty much my whole life. If I had a peak in my career, I was a service manager for about 8.5 years for a very, very large company where I'm licensed at. So enough about me. Let's move on here. I put this in here. It might seem a little odd to you, only because we're going to be talking about 454B, but I like to throw something in here every month just to kind of did you know, if you will. So moving forward, for everyone that's in the refrigerant world here, we're going to have 454A and 454C. Okay, B as in boy is going to be your air conditioning, A and C. The difference between A and C is A has a higher GWP, so that'll be for anything less than 200 pounds. C as in Charlie will be anything for over 200 pounds, okay? It has a lower GWP than 150. But notice at the bottom is what I really want to show you here. The thing about the blends when they're the same number is it's the same components, they're just changing the ratio, okay? So on this 454A, you can see it's 65-35, 454B, it's 31.1, 68.9, and so on and so forth. It's really about how low do you want to go? How low do you want the SST, as we say in the world, or suction saturation temperature? So that's where we get this, the 454A, B, and C, just so you know. All right, let's get started with the 454B presentation. A closer look at 454B. We're starting off with a chill zone poll question. So Chris, do you have that question set up?
All righty. All right, so the first poll question that's up is your branch actively selling A2L HVAC equipment? There's a lot of OEMs that are transitioning right now. They're starting to do their soft launches, or maybe they're doing a hard launch. Maybe you guys are already engaged. Maybe you've seen mini splits sitting around. Maybe you're a Daikin rep. So whatever you guys are seeing out there is going to help us get some real information from you guys. So is your branch, the one that you work at, maybe not, maybe your company has 30 branches across the state or 200 branches across the country, but is your branch actively selling A2L equipment is the question. I'm gonna scroll over here, see if we can see the answers as they're coming in. Oh, Don, it is heavy on no, not yet. So 6% have said yes, it's 454B stuff. 6% is 32. 17% said yes, both 458 and 32. And that's going to happen with a lot of like unitary stuff's going to be 454B, but maybe the mini split line like Fujitsu's 32. So there's going to be a lot of stuff like that. But 72% are saying no, not yet. So that's a pretty strong response.
Yeah. Yeah, very good. That was awesome. Yeah, I was anxious to see what the answer was,
Yeah.
but awesome. Thanks for doing that, everyone. Chris, appreciate it there.
Sure.
All right, moving on here to the first part of this, taking a look at 454B, or known in the lab as XL41, meets the regulatory requirements, obviously, no ozone depletion. Again, that GWP number the EPA likes is 466. If you didn't know, in residential or comfort cooling, the cap is 700. It is mildly flammable. We've talked on that the first episode on the flammability parts. That A is the toxicity, which is no toxicity. The 2L is just the flammability. That L is short for the low flame propagation, or basically the velocity of it. It's a very close performance to 410A, as you're soon to see, and then compatible with most commonly used POE oils. And we'll get into that a little bit more. So some of the criteria of a refrigerant that I learned along the way is, does it do the work? First and foremost, it can meet all the other criterias, but does it do the work? Does it do the capacity? And next is it flammable or toxic? Okay. And then thirdly, does it meet the EPA regulations, i.e. GWP, ODP, things like that? And is it capable of repeatedly changing its state from liquid to a vapor and back to a liquid while maintaining its chemical stability? And that's a big one. Unlike motor oil, we automatically know going into it that every 3,000, 5,000 miles, we're going to change the oil in our car. That's not the case for an air conditioning system. In fact, I ask this question all the time in class. Raise your hand if you've ever changed the oil in an air conditioning system. And typically the answer is no. In fact, almost every time, because that's part of the criteria of getting the oil and the refrigerant right. And then lastly, does it have relatively high latent heat carrying capacities and low boiling temperatures? And those are crucial also, obviously. Latent heat just simply means hidden heat, which we find in our coils. And I'll go over that a little bit later. And then a low boiling temperature. Does it have a low boiling temperature? Because if you didn't know, most of the fluids on the face of the earth can be a refrigerant. Water is a refrigerant. If you didn't know, it actually has a refrigerant number of R718, but we all know what the boiling temperature is of water. It's typically at standard atmospheric pressure, 212 degrees, right? So that's not a very low boiling point, but we use it in chillers, we use it in boilers. It transfers heat very, very well. So let's move on to this. So we're gonna look at 410A. 50% of 410A is in fact R32, which is an A2L refrigerant, ironically. The other 50%, for that reason, is R125. And when I say for that reason is R125, the two biggest things, in my opinion, that does is it first makes it a A1 classification, because R125 is a chemical that's commonly found in fire extinguishers. So the way that works in a fire extinguisher is the same way it works in the refrigerant. Is what it does when it's exposed to air, it actually removes the oxygen or sucks the oxygen away, which you can't have a fire, right? So, and the other thing it does is it keeps the discharge line cooler, because without R125, R32 is known for running a little bit warmer. It's just the nature of the beast. Not all refrigerants run the same temperature on the discharge line, and R32 runs a little warm, but it's going to be a big player in refrigerants to come, and so is 1234yf, by the way. So it's a balancing act, if you will. Moving forward, we're going to R454B. Now we went from 2088 GWP to 466. That's a huge move for the EPA. Remember, that caps at 700, all right? But what did the scientists, the chemical engineers do in the labs to make this happen at Chemours? They bumped that R32 from 50% to 68.9%, okay? So they actually put more of that in there, and they circled back around with 1234yf, which is a very common refrigerant, a Chemours product, an HFO molecule that's used in every car sold today in the United States and made, okay? But But look at the difference in the GWP. It's not exact math, but let's just ballpark it because we bumped one up 18.9 and from 50% and so on and so forth. But let's just say, for the sake of not arguing, we lost around 1,400, if you will, of GWP, and all it was, the harsher of the chemical was that R125, keeping it being non-flammable and keeping the discharge line cool. And if you saw our first episode in the flammability, the comparison of flame, they are pretty darn close to one another. It's not exact, but it's really, really close. It's closer to a 1 than it is a 2, okay? And in fact, when it comes to the velocity, we'll get into that, the speed of it here shortly. So let's look on the PT chart. I love PT charts. If you notice in the box, you see the PT chart, you have your pressure on the left-hand side, your saturation temperature on the bottom here. And if you look at 410A liquid and vapor compared to 454B liquid and vapor, they run pretty much parallel. So it's very similar pressure temperature profiles, as I'll show you here shortly. And then thermodynamics is almost identical. It's really, really close. Similar material compatibility. What I mean by that is we already know what it's going to do in a system. R32's already been in our systems. We know it plays well with others. It's not going to eat the copper. It's not going to eat the aluminum. It's not going to chew up the windings and so on and so forth. And the same can be said for 1234YF, because if you didn't know, 1234YF, pardon me, is already in a lot of our blends out there already too, if you didn't know that. Exact oil types for 410A to 454B, that would be POE 32, so no changes there. And then similar system architectures as far as a DX system. There's going to be some changes internally on some of the compressors. Some of the Oldham coupling and the scroll sets are going to be slightly different materials. But other than that, the nature of the beast, the cavity of the compressor is going to stay the same. The biggest change for me is you're going to have a different pressure setting on the TXVs. So the TXVs are going to be slightly different, as I show you, nearly, even as close as they are, you're going to see that setting be slightly different when I get into the pressure temperatures here shortly. 454B again has a lower GWP. Just that move alone from 410A to 454B is a 78% reduction in global warming potential. That is huge. We want to get down to 15% of what we were using in 2021 by 2036. That's a big deal. Just in that area of the industry, 78% reduction. A1 is a non-flammable, low flame propagation, but can combust. And A2Ls have a lower flammability. And again, that L was added with the consideration of the speed at which the flame travels and the LFL. So this is something I did recently. I took the old mercury compound gauges off and I took a screenshot of this PT or pressure temperature chart digital app that I had on my phone. And I chose 454B, as you can see. And from my experience, the evaporator on comfort cooling typically runs somewhere between 40-45 degrees. Now that's a well-running system. That's not on startup or anything like that with a heavy load on the house. So I chose 119 PSIG on my gauges. This is the low side. So if you're using mercury gauges, I know you all know this, but this would be the blue side, or what we refer to in the field as the low side. So this is your indoor part. This is the evaporator inside your house. When we take the pressure PSIG at 119, we look at 410A, and in the same application, same setup, we're going to see about 40.3 saturation temperature on your gauges and at your evaporator. When it comes to R454B, you're going to be around 45.5. And R32 is going to run 39.2 or somewhere thereabouts. And don't hold me to the exact numbers, but these are really, really close, almost exact, if not exact. But that gives you an idea. The reason I show that is I think it's important, especially for technicians, which is who I primarily teach, is they're going to want to know what's the pressures, what's the temperatures, and what's the POE oil. So I get that out of the way right away. Now, the PT charts 101, as you know, as I just showed you, you've got your pressures over to the left-hand side. And then on the right of that, you've got a saturated liquid temperature. That would be your subcooling. And then you've got a saturation temperature, vapor, on the other side. That would be your superheat. So the red boxes, I put the different colored boxes on the top. So you can see the red boxes below that is your pressures. The light blue, if you will, is your liquid saturation temperature or your condenser subcooling. and then your, let's say orange, pumpkin color, saturated vapor, or your indoor coil. So that's your low side. This would be your high side. Again, coming down here to 119. Again, for 454B, we'd have 45.5. So you just match up, as you all know, your pressures to your temperatures. And again, we use the liquid saturation for the subcooling and the vapor for the superheat, as I said. Now, speaking of which, saturation by definition is the temperature that a fluid will phase change from a liquid to a vapor or vapor to liquid. Basically, it's liquid and vapor in combination, okay? Anytime you have a drop, 1% drop of liquid and 99% vapor, that in fact is saturated. You could take a tank off your truck and you're almost emptied it completely. As long as there's a little bit of liquid refrigerant there, that is saturated. And saturated is what we use for subcooling and superheat. So you can hook up your gauges to a tank with just a little bit of refrigerant in there, take a temperature reading on the side of that tank if you wanted to, somewhere around 70 degrees or so, or 80, something decent, and you could actually confirm that's in that tank, that refrigerant, set it for the refrigerant that the tank is. And that's a great way to calibrate your gauges if you didn't know that, by the way. I used this method for years and years and years on recovery tanks. But subcooling is, first and foremost, it's a liquid. So we're looking for it in the liquid line, okay? And the way it's defined is it's any heat removed from a liquid below its boiling point. So you take water, for example, I'll use water as the refrigerant, R718. Water boiling point is 212 degrees. If it was 211 degrees, that's 1 degree of subcooling. It's any heat removed from a liquid below its boiling point. The same can be said about superheat, but it's a vapor. So it's any heat added to a vapor above its boiling point. So in the case of water, or R718, that would be 213 degrees. That's 1 degree above 212. It'd be 1 degree of superheat. So subcooling, liquid, any heat removed from the liquid below its boiling point, superheat, any heat added to a vapor above its boiling point. And I share that with you because I want to walk through the system itself. So let's look at saturation. If we were looking at a PT chart here, and I set the gauges up for 454B, so the numbers should be fairly accurate. As you know, we're always going to want, whenever possible, we want to take our pressure and our temperature readings within 6 inches of each other. That's not always possible, and I understand that, especially on supermarkets. When we get into the 454A and C, you're going to have some type of aperture up by the coils, 200-300 feet away. But let's, for the sake of arguing, whenever possible, within 6 inches. So if you're doing it outside at the air conditioning at Mrs. Smith's house, you've got the port there and you take your temperature reading, okay? So in this condition, what it's saying is at 115 PSIG for 454B, I'm reading 43.7 degrees on the line with my fancy clamp there, okay? And when I go to the PT chart, it also says 43.7. So the moral of this story is, and that's why you see the little air bubbles in there with the liquid or vice versa, that refrigerant is in fact saturated. And where do we find saturated refrigerant? We find it in our coils. Okay, and it's also called latent heat, okay? It's hidden heat. And what I mean by that is that temperature I showed you earlier, 45.5, it stays that temperature the whole way through, no matter how much heat it absorbs, okay, at some constant pressure, all right? So it starts out primarily liquid, 75%, 50%, and then 25% until it boils completely off, and then it's total vapor. Here's your superheat. And this TXV bulb is actually picking up that superheat. It's communicating back with that TXV and so on and so forth. Same thing can be said with the condenser here. It's changing vapor back to liquid. So it's rejecting the heat and then it's condensing back to a liquid. Let's look at superheat. Where do we find superheat? Again, superheat is any heat added to a vapor above its boiling point. So what I did here is I've got using 454B again, I put my 118 PSIG on there. It says my suction line is 55 degrees outside the condenser, okay? And when I go to the PT chart, it says 45 degrees for 454B. When I subtract the two, I've got 10 degrees, and it's 10 degrees of superheat. Notice that the saturation temperature is lower than the line temperature. Again, it's any heat added to that vapor, okay, or the boiling point, above the boiling point, okay? So the PT chart would naturally be lower than what's leaving the evaporator, okay? It's really, when you do this, it's really what's inside the coil and what's leaving the coil, whether you add or you subtract. And here's where you'll find superheated vapor. The low side, this is low pressure, superheated vapor coming into the refrigerant, into the compressor, leaving the coil here. Okay, this line typically, as you know, will be insulated, comes across the compressor and cools it down, and then it raises the pressure, which raises the temperature, and then we have another superheated vapor, but this is high pressure superheated vapor, and we want it to be that way for a reason, the law of physics. We want it to reject out into space. It has to be warmer than ambient air. Now let's look at subcooling. Subcooling, again, we're going to the liquid line here, okay? And what I pulled up here is for 454B is 396 PSIG on the high side. And I took my fancy clamp-on probe there and I clamped it on the line within 6 inches of my pressure gauge, and I came up with 109 degrees. When we go to our PT chart, on our PT chart, it says 120 degrees. So the moral of this story is we have 11 degrees of subcooling. Okay, 11 degrees of subcooling. Here's where we'll find subcooled liquid. Now, I like to take it 6 inches within the pressure gauge, but I also, whenever possible, like to take it prior to the TXV, if possible. Now, there's not going to be a lot of difference here if it's in comfort cooling, because you know as well as I do, especially those of you at the counter. I mean, a small line set might be 20 foot, a normal line set might be 40, 45 foot. I very rarely got into over 50-foot line sets. Not that I never did it, I did it a lot, but that's not the norm typically in a residential home. So let's just say 35 feet for the sake of not arguing, okay? The reason I say that is there's not going to be a lot of difference from what your subcooled reading is here than what it is. But I'd like to take them in both places. For one reason here is we have to make sure we have a full column of liquid going into our TXV, or we have an inefficient system. If we have any vapor in there whatsoever, the system's not going to work right. So it has to be all liquid get in there. And we usually like around 5 degrees of subcooling there if possible. If there would be a big difference between these two, we want to start looking into why, especially if it's a new install. Maybe this line got pinched or something, but that's where we're going to find our subcooling here, somewhere there, again, in the liquid side. Now to bring it all together, okay, it's coming through. We're dropping the pressure through our TXV, or our pressure dropper, I like to say. We drop the pressure because we know then we drop the temperature, and hot likes to go to cold, right? It's the second law of thermodynamics, really in plain words. So this load from the house or the building, the commercial building, it absorbs into that refrigerant as it's traveling through 75% liquid, 50% liquid, 25% liquid. As it picks up that heat, on the back side, the air is cooler. We're not really making anything cold. We're removing the heat. We're heat movers. That's what we do. So we take that heat right here as it leaves. In a perfect world, the idea is to have nothing but vapor here, or superheated vapor. That's the name, hence the name superheated vapor. All right. So it moves down the suction line down here. Okay. Headed towards the compressor. Now, the first job it's to do, 98.9% of the compressors out there are refrigerant cooled. So the first thing it does is it comes across the motor and it cools the motor. And then it goes into, in this case, in the scroll here, it'll go into the scroll set, the upper and lower scroll set, and it compresses that. When you compress those molecules, they start moving really fast. They're pressing them in there. When they start moving really fast, it causes heat. So we're raising the pressure and raising the temperature, which is what we're trying to do. That's the science behind it. In fact, if you drew a line across here from the compressor to the TXV, everything below the line, that imaginary line, is low pressure, whether it's liquid or vapor. Everything above that line is high pressure, whether it's liquid or vapor. So we raise the pressure here, moving forward. Oops. And we head on down to the condenser here. Now, the idea here is to reject the heat out of the condenser. As we reject the heat, we start to condense. We're sucking the air in from the side of the air conditioner at your house. That's why it's always crucial, as you all know, to keep those weeds down. Don't have, if you have willow trees and those kind of things, keep that cleaned up as much as possible. And then it rejects the heat. But what heat is it really rejecting? It's rejecting a lot of heat. A lot of people will say in class, it's rejecting the superheat. Well, it is rejecting the superheat. It's rejecting the superheat. It's rejecting any superheat that we picked up here. The load, it's rejecting the load. It's rejecting the heat from the motor. It's rejecting the heat from the compression. So there's a lot going on there, okay? And it rejects it out into the air, rejects it where we don't want it, and it removes it from where we don't want it and rejects it somewhere we don't care about, is what I should have said. And then we move it down, it condenses, it goes in the liquid line, therefore that line is a lot smaller, hence the name condensed, and so on and so forth. And that's our system. Now, I just made this recently and I had some moving actions in here, but basically at a very high level, I don't want to get in the weeds here, but I do like to share little tidbits here. Some of you at your wholesalers might help design equipment. I know the OEMs do and those things, but most wholesalers have a person on staff that design equipment, especially in commercial refrigeration, and they'll use these enthalpy charts and different things like that. And this is a saturation curve, this what I'm going to call a thumbnail, because that's the way I like to teach. Inside this thumbnail, anything inside this thumbnail is saturated refrigerant. And remember what we said about saturated refrigerant? It's liquid and vapor in combination with each other. Gets outside on this side, it's vapor. Gets out on this side, it's liquid, okay? So it basically is our system, if you didn't know that. A lot of times it's real busy with a bunch of lines. You can't tell what from, you know, what saturation is from the other ones, and there's all kind of lines. It's got a lot of information for you, and we'll touch on that on another day. But basically it's the box. It's the four-sided box. The bottom line is your evaporation. This is your compression. Here's your condenser, and here's your metering device. This is your line here, which equates to the line over there from the compressor to the coil, the condenser from the TXV, and then the TXV down to the coil, and so on and so forth. If you didn't notice, up in there, left-hand side of our four-sided box up there is our bubble point, okay? It's leaving the saturation. It's all liquid over there. And then down below on the right-hand bottom side, you'll see the red dot, and that's our dew point for the superheat. And this is what it looks like in a real system, okay? If this was a heat pump, it just reverses itself from what I just explained earlier. It literally has a reversing valve in there, as most of you know. And if you ever go to see failure in a reversing valve, just a fun fact, check the solenoid valve, because I've been bitten by that more than once, and it's a hard task, and probably some of you are smiling right now, if not laughing, but it takes about 6 hands to replace a reversing valve, and I've done it twice, and it's not something you want to do on a regular basis. So make sure you check your coil out on top of that reversing valve. But the idea of what it does is everything that the air conditioner did, the cycle I just showed you, it completely opposite on the heat pump, okay? So the coil inside, we're picking up heat on the outside and we're pushing that heat inside. And yes, it doesn't matter how cold it is. The colder it gets, obviously we can't produce as much heat, but the way these things are moving right now with the hyperheats and all these things, it's really amazing how low they can go. I mean, it's incredible how far heat pumps. I've had mine for 25 years and it's not broke, so I'm not going to replace it, but I'm excited about the next step or the next chapter of a new heat pump. Now we're going to talk a little bit about the Chill Zone Pizza Party. Chris, you want to touch a little bit on this?
I do, and I appreciate it. Don, I was just real quick, going back to that last slide. I don't think your heat pump is ever going to die. I don't. I think you're going to replace it and you're going to keep repairing it for the next 100 years. We're going to be on it's just going to be all just like propane and oxygen in 2050, and you're still going to be running the same R22 system.
You're probably right. I had to repair it this summer, though, just so you know. Patty was gone, but I let it go for a couple of days, even though it was 90, but it was a contactor. But anyways, moving on.
Alrighty. Hey, pizza party time. So each month, if you guys are familiar, if you guys have been here before, you'll know that we give out we award a pizza party to one of the attendees here in the audience. It's a really cool thing that we like to do. We know nothing like food for the branch. Really, it makes everybody happy, right? So how this thing works is we pick a name with our random name selector, and we send out 3 pizzas. We get in touch with you. You pick the pizzas. You pick where you want it to come from, what the drinks are. We send you a box of swag, and we pick a date. It's actually a pretty cool production. We've done it a couple times now. Mr. Steve Wilson was our first one, and I believe he's in the audience today. Our one from, congratulations, Steve.
Congrats.
And then, last month was Mr. JB Boudreau, and I don't see him here, but good on ya. And this month's winner, Don, is Lauren Jett. And so we picked her name out of the hat this morning. And so Lauren, we'll get in touch with you, but you're this month's winner.
Congratulations. Do we have any sound effects in the back?
Yay! Whoa, pizza!
All right, congratulations. Congratulations. That's awesome. Send those pictures in after you have the party. We'd love to see them.
Yeah, definitely.
Yeah. Okay, let's move on. Now that we're through all the easy peasy stuff, and most of it is here, let's look at 410A and R454B and R32 next to each other and see what that looks like. Uh-oh, we got another poll question first. Chris?
All righty, poll question time. The next one is, does R454B have a higher or lower operating pressure than 410A? Please select one. This is what do you know? This is what we'd like to know, how familiar you are with it. If someone from if one of your customers comes up to you and asks you, says, hey, what's the story with this stuff? Am I gonna, are my pipe's gonna blow up? What's your response? Like, do you know if it's higher or lower pressures? So that's really the question here. It helps us understand more about what emphasis we need to put on what information, what your comfort level is, that kind of thing.
Yeah, curious to hear what you've heard.
Yeah, yep. Early on, Don, that was the really big feedback. At the transition from 22 to 410A, I was hearing stories about people thought they were going to lose an eye. There was, all the high pressures. It was going to be ridiculous, and so that was a big concern for me.
I was that guy. I stayed away from our 410A equipment and I know a bunch of people are out there chuckling because a lot of us did it. But yeah, we never saw those pressures before. Good point.
That's funny. All right. Well, as far as results goes, we've got 59% people say it's lower, and Don, 41% of the people say it's higher.
Nice mix there.
Yep,
okay. Well, let's get it on. Thanks, Chris. I appreciate it.
Of course.
Let's look at it up close here. So we're going to start with capacity at the top here. Okay. And when we look at capacity compared to 410A, 454B is going to run slightly lower at 155. R32 is going to run slightly higher at 174. Now, of course, you always want great capacity, but when you do the math on that, it's about 2%. You lose about 2%. What I will share with you here is COP. And COP, if you didn't know, is the coefficient of performance. What the heck does that mean, Don? Well, simply put, coefficient of performance is the whole system as a whole. And this is why I think a lot of, if not all the OEMs really liked it, besides the GWP factor on this, is because the higher that number is, the higher the efficiency of the system. This doesn't mean any of these other refrigerants are bad. It's just the nature of the beast. And in my terms, the Don Gillis terms of explaining COP, it's really what they're doing there is they're calculating how much capacity you're getting out of your evaporator compared to how much energy you're using on, how much energy you're using on your compressor or the system as a whole. Overall, that's what they're doing there. That's the combined. So the higher that number, the more efficient the system is with that particular refrigerant, okay? Hopefully that made sense for you. Fire those questions in there if you didn't understand. Sometimes I don't explain things very well. So please, 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 if you have any questions, don't leave them on the table, put them in the box. Suction pressure, everyday business, boots on the ground. If you're seeing 130 at 410A, you're going to see around 117 or thereabouts at 454B. 133 on R32, it's going to run a little higher. Also on the high side, you're going to see 419 on 410A. In the same application on 454B, you're going to see 395. So we're, again, the folks that said lower pressures, you were spot on. On R32, it's going to be a little higher at 430. When it comes to the discharge line, on 410A, 6 inches out from the compressor, we're going to see about 167. On 454B, it's going to be about 177, and then R32 is going to be about 195. Remember, we removed that R125 from the 410A, so it's going to run just a little bit warmer on there, all right? So R32 naturally runs a little warm by itself, okay? So when we look at advantage of the lower mass flow, we're going to have a lower mass flow moving with 454B. So when we compare this with 410A, the benefits of a lower mass flow is it's lower energy consumption. A compressor does not work as hard, as I said earlier on the COP, with a lower mass flow. which lowers energy consumption, especially in low temperature applications where the compressors are more robust. They work much, much harder in those low temperatures. It has like a 10-to-1 compression ratio as compared to a 3-to-1 on the air conditioning system, okay? The higher that ratio number is, the harder that compressor is working. It's more stable system operation. A lower mass flow can help maintain stable temperatures and pressures, preventing excessive wear on the components. So those are just a couple benefits of the lower mass flow, and you can see that's what we have with 454B. And this just shows two different applications. We have AHRI testings here. This is 82 degrees outside, and this is 95 degrees outside. This I threw in here from my Copeland days. This is what we call curve charts. Or performance charts now. We used to call them curve charts. I'm showing my age. This was something we used to drive around in our trucks before the digital age, and they would be in a binder, and they would be, the color of the paper would be the color of the tank of gas you were working on. And you could bring your fingers together to the condenser pressure and the evaporator pressure, and you could see what the temperature was. On this particular curve chart, when we do that, what we're seeing is the C is telling us the capacity, BTUs per hour. The P is our power, or watts. The A is our current, or amps. And then M is the one I want to get to, and that's mass flow, pound per hour, okay? So for example, if we move this to 35 degrees, just left of the 35, 45. So the 45 degrees is the temperature of the evaporator. The 130 is PSIG is your gauge, and the same can be said down here. 477 on gauge pressure. This is 410A, by the way, is going to be about 130 degrees on your condensing temperature. If you were to lower your evaporator pressure or temperature and move it over just one box, you can see our mass flow, what it does. It actually goes up a little bit on here, okay? Or lowers, pardon me, it lowers down here. So you see what happens here. And the same can be said if you go up higher here, or lower, pardon me, with the condensing temperature, you can see what happens to our mass flow there, 564 compared to 559. So it's a nice way. I use these a lot in my earlier years for just little things you can do with technicians in the field. So by putting these numbers or bringing their fingers together in class, they can actually see how amps are reacted, or the capacity, or the mass flow, or the EER, and those kind of things. So it's really, really cool, and they're free, by the way. You can just print them out. Okay, so let's look at some temperature glide. Temperature glide is going to be pretty much the same. I see a lot of things out there about glide, and 454B has glide. It does have glide, but you're not going to take in consideration, and I'm being straight honest with you. 410A had glide also. We never talk about it. It's less than half a degree. You will never talk about it in 454B. It's 1.4. Now, before you hold me to that 1.4, it's going to depend on whether it's in air conditioning mode or heat mode, or what that glide is, because it will be different, just so we know, okay? And glide simply means that the chart on the right-hand side, as I show you here, you can see glide. A blend is defined by anything with two components or more. And the glide is simply the different boiling points of each one of those components. So the farther those boiling points are, the more glide you have. The more components you have, let's say you have 4 or 5 components in one blend, and there's a lot of them out there, you'll see more glide, because it's the difference between your first boiling point start and then your last boiling point. And the way it works is it's still in a blend form, but the highest pressure or most volatile component in that blend will start to boil off first. In other words, it's changing state first from liquid to a vapor. It's still staying in contact with the blend. It's not fractionating or breaking up, okay? So the molecular weight, I don't spend a lot of time on that. Here's our boiling points to give you a comparison: minus 60.6, minus 58.6, and minus 60.9. The oil, as I said earlier, for 410A and 454B is going to be POE 32. Again, not that there's anything wrong with this, but R32 is going to run a little warmer, just like an automobile. It's going to need a heavier or higher viscosity of oil, so it's going to need a POE 46. If you want to double check my work here, go to Application Engineers Bulletin 93-11 on Copeland's website, and you'll see all the oils and all the refrigerants and what applications they're allowed in on the front side of that sheet. Okay, and all compressor manufacturers have them, and you'll see POE 46. Global warming potential, we kind of hammered that out pretty good. 2088 for 410A, 466 for 454B, and 676 for R32. Remember, that cap is 700 right now. Now, will fractionation be an issue? You know, I'm not going to spend a lot of time on fractionation because I don't want to muddy the water here, but we were taught years ago how crucial it was if it starts to leak, you know, and I've seen people get in arguments on job sites before. Oh, it's more important if it leaks from the liquid. It's more important if it leaks from the vapor. Quite honestly, it makes no difference. And if you didn't know, any blended refrigerant fractionates every time it shuts down. And where it does this at is in the coils. Okay, it's going from liquid to saturation to vapor. When it shuts down, that's fractionation, if you didn't know that. Worst scenario would be a very small leak inside of an evaporator over a time of completely retopping it off. And that's not something we want to get in the habit of doing. If you have something you know knowingly has a leak, one, twice, and you'll see this moving forward in the AIM preparing those leaks, by the way. It's going to be in writing now. But fix the dang leak, remove the refrigerant, do the right thing and fix your leak, okay? All right, moving on forward to the next one, myth versus fact. Myth versus fact. If a leak occurs, the service tech will need to remove the entire charge and make the necessary repair and recharge. I just touched on that. It's about fractionation. In a lot of the installation manuals when 410A came out, it said in writing, if you get a leak, you need to take the whole charge out, or tech support would tell you that, and then weigh it back in. And nowhere in that pamphlet did it say you can't use the refrigerant you just took out. It was kind of a little sneaky thing that you had to catch in your early years, but it's basically telling you what they were really doing is blended refrigerants were new to all of us. POE was new to all of us, including engineers out in the field or tech support people. So if you've ever been on tech support call before, which I have many a times, and some of you are probably tech support that are listening in right now, one of the first things you do when you don't know where someone's at is, or one of the things you do is, hey, why don't we pull the charge and weigh it back in, especially on small charges like geothermal units or mini splits and things like that, critical charge units. Those are key. So again, the 454B is classified as a zeotrope, and it does have glide about 1.4 degrees, if you will. Again, it's going to depend on whether it's air conditioning mode or heat pump mode. R54B is a drop in 410A. Absolutely not. You will not be able to put any, I repeat, any A2L refrigerant in an existing system. It's not, doesn't have the safety features in it. It'll be against the law. You just don't want to do it. You don't want to ever mix refrigerants, obviously. I think that's kind of a no-brainer because what you're doing there is you're literally creating a new refrigerant, a Frankenstein refrigerant. And then I always ask the class, how good is my PT chart now? Because my pressure temperature relationship is based on the components that are in that blend. And if I mix something, even no matter how close it is in pressure temperature, you're gradually throwing that off. So just don't do it. 410A will still go in 410A systems. 454B will be used only in new equipment designed for 454B, okay? All right, myth or fact, all service techs must be recertified. That is not correct. All service techs that hold EPA Section 608 certification will be grandfathered in and will not need to take an additional exam. Moving forward, just like they did with 410A, it's identical. You will then have C questions about A2Ls on the test moving forward. Do we think at Chemours you need to be trained? Absolutely yes. We are definitely a big advocate for training. We do it all the time. We get people certified all the time. We have a large team of salespeople, marketing, myself, and everyone else, webinars like this training here that gets you certified for that. But as of right now, if you've heard anything differently that, hey, the EPA is going to require you to retest on that, it's simply not true. Myth or fact, when replacing an existing residential or commercial central 5-ton split system, you must replace the refrigerant line. That is not true. So when you're moving from these refrigerant lines from residential, let's start with residential, okay? Residential lines, as long as the sizing is the same as the new equipment is, you are allowed to use it, the lines, okay? They're going to ask you to check and confirm that it's installed the way it should be on a new system, striker plates and those kind of things. The last thing, at the very least, we need to do, at the very least, is to pressurize that line and let it hold for an hour. That's a new part of the standards now. Okay, it holds, and it's an ASHRAE 15.2 for residential, and it's an ASHRAE 15 for commercial. You're going to hold that pressure on there. When it comes to commercial, I'm going to go off topic slightly here on refrigerant lines. The big difference there is you're going to have to mark the commercial lines, and I mark that on there, and it goes into pretty depth, but I'll just put it like this. You have to mark, whether it's existing or new lines, you have to mark on there that it's an A2L refrigerant on the side of it. And then it goes into how many feet you have to mark that. Okay, and there's certain increments, and you have to read that in 15.2 or 15, pardon me, ASHRAE 15, because it's not in 15.2. It's only in commercial lines, because I've gotten this question many times over. Hey, someone over here is saying that you have to mark the lines with a red tape or red dot. That's not true. What they're talking about is, and those letters, by the way, actually have to be a certain size. They can't be less than a ½ inch tall. So just some fun facts there for you. If you have questions about this or anything after the fact, if that didn't make sense to you, put it in the box or make sure you reach out to us afterwards, okay? Let's talk about our resources. Hey, first of all, we got another poll question. Chris, do you want to give the last poll question?
I do. All righty. Question: what is your preferred resource type to leverage when your customers ask you questions about refrigerants? Okay, this is kind of a fun question for us, because we've got a lot of our own channels and stuff like that, but we really want to know what works for you guys. If someone comes in and says, hey, zeotrope, non-zeotrope, I got to know, where do you send them? Maybe they're not asking you specific refrigerant questions, but with questions that are related to this kind of thing, where do you go? Do you go to like your favorite YouTube videos? Is there I hate to say TikTok or Instagram, but is there a content producer or some kind of influencer that you send people to, or do you send people still to the tech support phone numbers, right? So how do you handle when your customers come in and ask you for information about refrigerants or other technical things that you don't maybe have the information for? Like, how do you handle that?
I know what I would say, and I'm assuming a lot of technicians, I can't speak for everybody, but the good old Google machine works great in situations like this. And most contractors are self-sufficient, and counter people are too. They'll hunt that down and get good resources. But I'm curious to see what the answers are on this question. This is a great question, Chris.
Yeah, I think so too. And you're going to like some of the results that are coming back. So 41% of people are saying videos, right? So that's pretty handy. Videos kind of like this, probably. Thumbs up, Don. 41% also said refrigerant app, right? So I know that you've introduced me to a couple good apps that are out there. I'm not going to name them, but there's some good ones. Let's see, 12% said tech support phone numbers. It's still a hot item, still a reliable source. And then 6% said this doesn't really come up, right? So if only 6% of the people out there are not getting questions about refrigerants, that's also kind of good to know. So let's talk a little bit more about what we can offer them, Don. What do you think?
Yeah, so the first thing that comes to mind for me and that we teach in the classroom is, when in doubt, go to the OEM, go to the manufacturer. So in the case of refrigerants, I'm a little biased, obviously. I'm gonna have you go to Opteon.com, okay? And you can find all kinds of information. That basically everything that I showed you here today and that we've shown you through all these chill zones can be found on Opteon.com. We have tech support in there. We have all kinds of things. And I'm gonna get into that in the next slide or two, but go to the manufacturer's websites. It's amazing how much information they have. If I want to know about compressors, I go to the compressor manufacturer. I want to know about TXVs, I go to the TXV manufacturers. But yeah, there's lots of great resources. The takeaway for me is there's just so much information out there. Just make sure you're getting it from a reliable resource. All right, moving on to the next word. Hey, ironically, A2L refrigerant resources. Some of them that I like, hopefully I didn't forget. I know I forgot some people. This is just a handful of them, so I'm not here to offend, but because all the wholesalers have great websites also, and I know this for a fact, but I didn't want to name names. AHRI is a great place. ACA is a great resource. The HVAC School podcast I really like. All their stuff is free. ESCO has some good information on there, some great information on there. Some of that, if not all of that, you have to pay for, but they have some great free videos too. RSES, I'm a member. I've been a member for a long time. Great resources on there, monthly webinars. Copeland has some good resources. Obviously, I just came from there not long ago. And then Field Peace and Field Peace's competitors. I should have threw more of them in there, but just to name a few there. So, and I'm sure you're all aware of them, but this is just something I share in class commonly to get more resources on A2L refrigerants and anything else. It seems like everybody's talking about A2L refrigerants right now, right, Chris?
Everybody.
Also, a little bit off topic of A2L, but not so much. If you work in the warehouse or you store a lot of refrigerant at a contractor's building, here's one that we get occasionally, not as much as we used to. So what is the rack? So this hasn't been put into to any code books just yet, but this comes off the AHR website, and they're moving this towards the code books and the fires and marshals and what have you. But if you want this trifold, simply go, again, I'm going to throw Google out there because it's the easiest way that I found to do it. Instead of copying that big long link on the left-hand top side, simply put AHRI, A2L, storage. If you just put that in the search engine, this beautiful trifold, colorful thing will pop right up on that. I literally popped the PDF up and put it on this PowerPoint. It's real simple, kind of gives you an outline of what that looks like if you have any questions on there. Again, this has not been put into the code books yet at the state level, the municipalities or anything like that. This is what the AHRI is proposing, and this is what they're trying to get input, our people, other people, all those people around the nation. So everybody's kind of singing from the same hymn book, if you will. Okay. All right. Last but not least, our resources. You can go to option.com, as I said earlier. We've got all kinds of stuff. The team behind the scenes right now that does all the hard work, Chris included, is doing a lot of work with our website right now. There's just so many people doing good things out there. We have some great stuff on there. It's amazing. If you haven't taken a peek in lately, please do. Go to option.com. You'll see all kinds of stuff. I didn't have the right slide in here, but if you go to the sales and education part on the top of the screen, you'll actually be able to touch on that. You can actually go to option.com/training. Remember that, option.com/training. I need to update this slide. And that'll take you right to our training page with all kinds of resources, everything you can think of, PT charts, data sheets, everything you need to know. All kinds of literature, tech support, the phone numbers, Dr. Chuck videos here. Check up with Dr. Chuck. If you haven't seen Dr. Chuck, option.com YouTube channel, that's where you'll find these Chill Zone episodes on, by the way. Go there. Obviously, follow us on YouTube, Facebook, and LinkedIn. I follow all of them. Good information there, just to name a few. All right. Now we will take questions. I ran kind of long, and I do apologize.
That was awesome. I appreciate it. Never an issue. We do have one good question. It's from a gentleman named Barry Kepner. His question is, Don, do you feel that the new A2Ls will be able to be recovered and repackaged as 410A and prior HFCs?
Well, first of all, hi, Barry from Meyer Supply. Barry's a friend of mine up there. Nice. And so, yes, I see the same thing happening, Barry. That we have with 410A, the same process. We're going to be reclaiming that, recovering that, reclaiming the refrigerant back out, and you'll see the same thing as moving forward as it is. The difference here too is, and we'll get into this on another day, is somebody shot me an email this morning about this from another wholesaler. The recovery tanks, if you haven't heard, are also going to have red stripes on them, and they also have decided to go with left-hand threads. That's, I say hot off the press, but that's within the last 3 months. They're actually being manufactured right now as we're speaking. So I haven't seen any out in the field yet. Hey, by the way, if you're at a wholesale branch right now and you've seen the recovery tanks or you've gotten some in, share that with us in the chat room, because I know they're being mass produced right now, but I haven't heard of anybody actually getting one. We all saw one at AHR last year as a demo, but that's the only one I've seen. But yes, I believe it's going to be business as usual. I don't see it being any other way. Great question. Thank you, Barry.
Let's see, we just got another question in from Mr. Arthur Williams. He's wondering, well, will the low mass flow have any effect on oil return with long piping runs? That's a good question.
Yeah, it's a great question. And really it's going to come down to it could, but really where that's going to be key at is the designer of the equipment. So I have an article out there if you care to look into it. It was wrote uh, while I was at Chemours for the Tech Tips on HVAC School, but it's if you just Google Don Gillis oil trapping, I don't know how many people have reached out over the last 2 years. That was a very popular article, but it's really going to be on knowing your riser distance, size of piping, the length, the fall. We typically want a 1/2-inch fall in the direction the refrigerant's moving and those kind of things. Risers, typically, if you talk to a compressor manufacturer, they're going to say 20 foot. Some case manufacturers say every 10 foot, they want a trap in there in your riser. Again, compressor manufacturers typically say 20, whatever the case may be. You may be reducing down to a smaller size, but it's really going to be based on that. And then will you need a mechanical oil return like an OMB or an OMC or something like that, the electronic type, if you will. So great question. But if the design is proper, you shouldn't have any issues because there's a lot of refrigerators out there with very low mass flow. In fact, a lot of them in the cold applications, minus 35 evaporator temperature and what have you. Great question. Thank you.
That's the last question that we do have. Just wanted to add on to that a little bit though. With the my experience, I come from VRF systems, mini splits, before I came and worked here, and systems that like VRF systems that have very long line runs and stuff like that. All of that is designed and built into it based on the refrigerant and on the oil, right? PVE oil, maybe it's not POE, maybe it's got a lower viscosity. So the equipment is also going to take that into consideration, and so the OEM is going to give you proper guidance on what to look for if you're dealing with some kind of system that's already been pre-designed. Maybe it's not commercial refrigeration, but maybe it is a VRF system where you're given limitations, line lengths, that kind of thing. So
yeah, and that's a great point, Chris, and I'm glad you brought that up because I don't want anybody walking away confused. As far as the 454B, that's not going to be a play. What we call high temperature or comfort cooling, it's where you see issues like that where evaporator coils get logged and things like that is typically poor design, airflow issues, and those low temperature applications is what, from my experience anyways. But yeah, great question.
Oh, good deal. All right, we got a couple more questions that just came in.
Okay.
It looks like from Mr. Jose Armas. Question is the 454B and 32 cylinders different, being that the pressures are higher? I guess that's the first question. Oh, okay. No, it was the second part was just I confused the second part. But that's the question. Is the 454B and 32 cylinders different, being that the pressures are higher?
Okay, so I can't speak to the R32 tanks. I would be assuming, and I don't like to assume, but as far as the tanks for, let's say, recovery for 410A and 454B, the thickness or the mill of the tanks are the same. The same will be said for the 454B and the 410A. That I'm really confident telling you that. The difference here will be, one big difference will be the density of the refrigerant. So if you were buying 410A at a 25-pound DAC or disposable container, if you will, the 454B is going to be the same dimensions. It's going to look the same. It's going to fit in the rack the same on your truck, but it's going to be 20 pounds. And it's not like buying a bag of chips where they filled it up with mostly air. I don't want you to think you're getting ripped off. It's the density of the refrigerant, just so you know. Okay, so R32, I honestly don't know what that density is. I should probably know the answer there, but I don't. I don't know what that poundage is on there. So as far as the tank designs, R32 should still have the red stripe around it, will have it, and it'll also have the left-hand threads also. But as far as the pressures, you know, those pressures, those spring pressures that they've decided to go to replacing the rupture disc, someone reached out again, another question. I get quite a few questions. I got this one this morning also. Somebody, one of the wholesalers, said they got a question in class. What's the exact pressure that it goes off on 454B? You really can't answer that. I mean, I know the answer, fairly close to it, but you can't speak for all A2L refrigerants or any refrigerants, because every refrigerant, as you know, has a different pressure temperature relationship. And a lot of times we use temperature as the way we express that. But honestly, a lot of people throw 130 degrees or 125 degrees. That number stems from storage temperature. Okay, that's where that comes from. But really, it's based on pressure. And depending on the pressure of that refrigerant in there, because every refrigerant with different components in it's going to have a different pressure relationship. So that's going to be designed for that relief valve on each one of those tanks. So they may vary. I know they'll be different for 454B and 410A for sure.
Thanks a lot, Don. I appreciate it. Now, technically, we are at time, but we can maybe answer this next question before we wrap off. Let's see. Quick question is from Mr. Jeremy Burrows. He's asking if the density is higher, are the charge weights close on systems of the same capacity?
Jeremy, I'd like to give you a pizza party too. What a great question. I wish we had another hour. So I'm glad you brought this up because I reached out to a guy named Bobby Dean. I said, hey, they're going to want to know this. He goes, why are they going to want to know this? Blah, blah, blah. So to answer your question, if you're using the multiplier, let's say you have a line set of 3/4 inch and 3/8, 3 on the suction side, 3/8 inch on the liquid side. We use the multiplier of 0.60 for 410A now. When we use R22, it was different. If you're using 454B, if you want to get down in the weeds and be perfectly exact, it's going to be 0.55. Great question. Great question. Okay. So if you use 0.60 by accident, you're going to be really, really close. But if you want to get down there and dial it in perfect, it's 0.55 ounces per foot. If it's a 3/4 inch, 3/8 line set. If the line set changes, obviously that point changes. Okay. Thanks a lot for that question. You ended on a good note.
Good deal. Thank you, everybody. We are at time and we are going to close it out. We appreciate y'all participating. If you guys know of anybody else in your organization that would benefit from these, maybe they're just not getting our invite, forward it on over to them. Let's make sure that they're getting invited over to this as well. Again, we hold this thing the first Tuesday of every month, and we are going to for the foreseeable future. Alrighty. Thanks a lot, everybody, and thank you very much, Don. I appreciate it.
Great job, Chris. Thanks, everyone.
Thanks, guys.